Hey everybody, this is Lucas Bennett, and this is my lab number 5. Okay, so last time we studied objects that had a net force of 0, but this time we're going to add in gravity and drag. We're going to start with just gravity, and in a little while we'll add in drag. So for my models, I had a hacky sack and a popcorn bag. The popcorn drag was the one that's supposed to fall slowly. This is the positive x-axis, and this is the negative x-axis. I set the calibration stick, and I set the weight of the object. And I set the middle of the object just to be the middle of the ball in the bag the best that I could. I'm going to play the video. You see that it accelerates in the negative y direction as we would expect it to. Plots it over here and puts the data points. And over here you can see the popcorn bag, and it did pretty much the same thing. Okay, so I want to show you the model that we did in VPython. The delta t was 0.033 seconds, and there were in between each clip and in between each shot, and there were 17 shots. So I multiplied 17 times 0.033, got 0.595, and that's how much time we did in our model. And once again, we have Newton's second law down here determining our velocity update and our position update as well. So when we run this, you can see that it accelerates in the negative y direction at a constant acceleration, and the velocity is increasing. Over here, we plot our data in Google Spreadsheet. This is the times, this is the actual y distances, and this is the theoretical based on an equation where only gravity is factored in. Over here, you can see the graph that I plotted, and you can see that this is the real, the blue. It doesn't follow this line, and that's because there's another force acting on it, drag. And this would just keep on accelerating forever and ever, and it would never reach a terminal velocity. It just keeps speeding up forever. This is the popcorn model, and you can see that it's really about to reach terminal velocity. It would pretty soon, in fact. But this, like the last one, it would just keep on accelerating forever and ever because drag's not involved. This is my graph where drag is involved, though, and you can see that they follow a much closer line. This deviation right here is because it was really hard to follow the ball in the video. It was really bad light contrast, and it's hard to tell where the middle of the ball was. But you can see that they follow each other pretty closely. And here's the popcorn bag graph, and you can see that they don't quite follow each other, and this is because the equation that we use to incorporate drag is not the correct one. What we do is in this lab, we treated it like it was a proportion of the gravity force, and so it's never gonna quite be realistic because drag is not that way. Because when you're moving slowly, drag doesn't really affect you, but when you're moving really fast, say you're skydiving, you can really feel the air beating against you, and you know that's a real force. But in this scenario, it's always just going to be a fraction of the gravity force, so it'll just keep on accelerating forever. It'll, in fact, never reach a terminal velocity because the forces are never going to equal each other because the drag force is always a proportion of the gravity force. So for the what if question, will it ever meet a terminal velocity? And that is no, because like I said, the equation sets drag equal to be just a proportion of the gravity, and so it'll never equal the gravity and cancel it out, and there will never be a constant velocity. Also, even if, for the what if question, even if we threw down the hacky sack to begin with, or the popcorn bag, our model would never predict there to be a terminal velocity, for the reason that I just explained. It would, in real life, it would reach a terminal velocity much faster, though, because it's already at such a high speed. Drag is already playing a bigger role than it would normally. But once again, our model will never predict there to be a terminal velocity. It'll just keep on accelerating forever and ever. And I think that's my lab. Thank you.